Hello, and welcome to the Sum and Difference Identities Day 1 video. So the past couple days we've talked about our quotient identities and our reciprocal identities, which we already knew, and our Pythagorean identities, and we've practiced with that just a little bit, but now we're getting into some of our new identities. So this is in identities, I call it like cheat sheet, using quotations, but just something you will be able to use on the test. This is a reference sheet, and you will not have to memorize any of these identities. We're not even going to be going over all of these. But I do advise to open up that cheat sheet, again, quote unquote, while you're working for the next few days, just so that you can look back at it and reference it. So for instance, we will be focusing on sum and difference over the next few days. So I have taken a picture of just this section and posted it on the Canvas page. Starting Monday and Tuesday, we will be dealing with the double angle and half angle identities, which you can see up at the top. Don't worry about product to sum. Don't worry about sum to product. Don't worry about sum of sine and cosine. Don't worry about Euler's formula. So we're really only doing about half of this. So I know it looks like a lot, so we're only doing about half of this. And you get to use this on the test. I will have this attached, kind of like I will have attached a blank unit circle so that you can use it to reference. But like I said, we're going to be focusing on these sum and difference identities, so I'm going to actually just focus in on that a little bit and move it up here so we can look back at it and reference. You may see me kind of shift the screen a few times so we can go back and take a look. But just keep in mind that when we are talking about our sum identities, we're taking a look at whenever we're adding. And we're talking about our difference identities whenever we are subtracting. Now you may notice here, this is a little different than what we had for our other identities where we used like theta. That's because we only had one angle involved. When we're dealing with our sum and difference identities, we're adding and subtracting things, so we need two things to add or subtract. So we'll be dealing with two angles, A and B. We might call them A and B. You'll see me use alpha and beta later, which are their Greek counterparts. But sum, remember, plus, difference is minus. So in the first example I'm going to give you, we're going to do 4 examples today. This first one, there it is. I'm going to ask you, find me the exact value of cosine of 75 degrees. And you'd be like, Miss Twain, that's not on my unit circle. I don't know what I'm supposed to do. Well, I'm going to ask you in this case to use your difference identity. So we're going to look for our difference identity, so that means minus, and this is a cosine. So we're going to be using our difference identity of cosine, so that's this one right here. Except now, instead of having an A and a B, I just have 75. So I have to figure out, okay, well, how can I split 75 into 2 different angles where I'm subtracting? And you're going to want to split this into 2 angles that we know from our unit circle. So I'm going to split this up into cosine of 120 minus 45. And I do this because 120 minus 45 gives me that 75 degrees, and we now have our angles A and B. So when we set this up, instead of using A and B, I'll use 120 and 45. So I'm not going to use negative 45, I'm just going to use 45 because that negative or that minus is part of the equation. So this will become cosine of 120 times cosine of 45 plus sine of 120 times sine of 45. So if we take a look at this identity here, we have cosine of angle A minus B, or 120 minus 45, is equal to cosine of A times cosine of B plus sine of A times sine of B. So that's kind of where that angle A and B come from. But now that we have cosine of 120, cosine of 45, and so on, those are all things on our unit circle. We know that stuff, or at least we should. So feel free to have your unit circle out at the moment if you need it. But let's write down what we know. Cosine, or the x value at 120 degrees, is negative 1/2. And then cosine of the x value at 45 degrees is the square root of 2 over 2. So we're going to take these two things and multiply them together. And we're going to add that to sine, or the y value at 120 degrees. which is square root of 3 over 2, and sine of 45 degrees, which is the square root of 2 over 2. So these things are going to be multiplied together and added to our other pieces. So let's see, if we multiply that first part together, we get negative 1 times square root of 2, which is negative square root of 2, over 4, plus, let's see, square root of 3 times square root of 2 is square root of 6. You can multiply those together because they're both under the square root, over 4. And then when I add these together, I'm going to get negative square root of 2 plus square root of 6 over 4. I can't combine the negative square root of 2 and the negative square root of 6 because they don't have the same base or the same number underneath. So this is where we end. This is the exact value for cosine of 75 degrees. So let's try this once more. What if I ask you the exact same question and I ask you to find me the exact value of cosine of 75, but instead of using our difference identity, we use our sum identity, or use the identity where we are adding. So if we said, again, cosine of 75 degrees, but now we're going to use our sum identity. So I need to find two angles on my unit circle that add up to 75 degrees. And there may be different variations of this depending on how large or small the angle is, but with 75 degrees, there's kind of one really clear choice, and that's going to be cosine of 30 degrees plus 45 degrees. So 30 degrees and 45 degrees are on our unit circle. They add up to 75, and they're going to be our angle A and B. In this case, since we're adding, if you did like 45 is your angle A and 30 is your angle B, that's still going to give you the same thing. So if we take a look at our cosine sum identity, we're going to break this out into, I'm going to move this up just a little bit. There we go. This is going to be cosine of 30 degrees times cosine of 45 degrees minus sine of 30 degrees times sine of 45 degrees. So for our cosine sum identity, we have cosine of A times cosine of B minus sine of A times sine of B. So we have those specific angles there. So again, now we've had our identity, we get to use this identity on our, or we get this sheet on our test. It's going to be really important to know that unit circle. So cosine of 30 degrees is going to be square root of 3 over 2. Cosine of 45 degrees, square root of 2 over 2. We're going to multiply those together and subtract sine of 30 degrees, which is 1/2, times sine of 45 degrees, which is square root of 2 over 2. So order of operations, we have to do our multiplication pieces first. So this is going to be square root of 3 times square root of 2 is square root of 6 over 4 minus square root of 2 over 4. And we end up with the square root of 6 minus square root of 2 over 4. And when I take a look at this, I'm like, Miss Twain, this answer's the exact same thing as this answer. It just looks different. Yeah, and you're right, they should be. I'm asking you the same question twice. We're just doing it in two different ways. In both problems, I asked you to find the exact value of cosine of 75 degrees. Whether you're using your sum identity or your difference identity, you should be getting the same thing. So we have our difference and our sum. We're getting the same answer. They just look a little different. So sometimes I will say, hey, use the sum identity to do this. Sometimes I'll say, hey, use your difference identity to do this. Sometimes, like in our next problem, I'm going to ask you to just choose. You get to pick whether you want to do your sum or difference identity because I know you'll be getting the same answer. So we'll do one more example like this, and then we will go on to a proof. So I'm going to move this off to the side. I'm going to move this off to the side so we can see our identities. And we're going to do example 3 as sine of 5 pi over 12, because you can do this with radians as well. So I'm going to say pause this here and choose. Would you like to use your your sine sum identity or your sine difference identity? Pause for a moment, try this out, then you can see what I do. Okay, so hopefully you're back. I'm going to be using my sum identity when I do this, literally just because it's the first equation in the box. You should be getting the same answer either way. But when I break out something like this, I might go, okay, I don't really know how to break this up. What if I try 1 pi over 12 plus 4 pi over 12? Well, 4 pi over 12 reduces to something we know on our unit circle, but pi over 12, okay, that's not on our unit circle, so we have to try again. So I'm going to go back. Let's break this up again. Let's see if I do 2 pi over 12 and 3 pi over 12. These can reduce. These are going to become sine of pi over 6 plus pi over 4. And these are on our unit circle. So if you kind of have to guess and check a little bit with your sum and difference, kind of play around with those degrees or radians about finding things that add or subtract to the specific angle, that's okay. So anyway, we get to here and we have our angle A and our angle B. So when we do our sine sum identity, that's going to be sine of, let's see, pi over 6 times cosine of pi over 4 plus cosine of pi over 6 times sine of pi over 4. So, or as you can think of it, sine of A times cosine of B plus cosine of A times sine of B. So we're just taking our angles, we're replacing them that way. You don't have to draw in the A and B if you don't want to. It may help. You can color code, kind of do what you need to do. But again, now that we've used our identity, knowing our unit circle is going to be very, very helpful. So let's see, sine, or the y value at pi over 6, is 1/2. Cosine at pi over 4 is square root of 2 over 2. So we'll multiply those together, plus cosine, or the x value at pi over 6, which is square root of 3 over 2, times sine of pi over 4, which is square root of 2 over 2. You're going to get that a lot. And see, once we multiply these together, we get square root of 2 over 4 plus square root of 6 over 4. The more you do these problems, you'll notice that you're going to get the same types of answers over and over again. When we add these together, we're going to get square root of 2 plus square root of 6 over 4. And this is our final answer. So if you used the sign difference identity when you paused and went through, you should still have the same answer, or something like this. You might have square root of 6 plus square root of 2 over 4, which is the same thing. If you do, awesome. If not, maybe go back and check your work. So anyway, you can use these sum and difference identities with your unit circle to find values that aren't necessarily on the unit circle. But we can also use them for our proofs, just like we've been doing with our other identities. So I'm going to throw one proof up here just so you can kind of see how they might be used, and then we can practice them tomorrow. So make sure to have this out by you. I am going to be moving away from it, but maybe open up a screen next to you while we work on our last example for the video. And this is what I'm going to be bringing out, alpha and beta. Feel free just to use A and B. So the sine of alpha plus beta over cosine of alpha times cosine of beta is equal to tangent of alpha plus tangent of beta. If you're wondering why I'm using alpha and beta in this instance, it's because, again, the sum and difference identities only work if there are two separate angles, so we need to identify an alpha versus a beta. Also, I grabbed this problem from the textbook, and they used alpha and beta, so when I did my notes, I also used alpha and beta. But again, if you want to change these to A and B, that's perfectly fine. So I take a look at this, and I go, okay, these don't seem to be any particular identity, but sine of A plus B, or sine of alpha plus beta, that's an identity. So I know I can expand that out. So I'm going to be picking my left side over here and say that sine of alpha plus beta over cosine of alpha times cosine of beta is equal to, remember you can take a look at your identity sheet, sine of alpha times cosine of beta plus cosine of alpha times sine of beta over cosine of alpha times cosine of beta. So all I've done is I took my sine sum identity, I expanded it out, so this is what we have. Now I look at this and I go, wow, that's so many letters. It's beautiful. This is what math is to us now, just letters, no numbers. But even though there's no numbers, doesn't mean the thing that we already know about numbers doesn't apply anymore. All the math rules that we know still apply. If you're like, Miss Twain, I have no idea what you're talking about. I'm talking about fractions, because right now all I see is a real giant fraction, but I'm not supposed to end up with a fraction, right? Like I'm supposed to end up with like two separate pieces here, and right now we have one. So I'm gonna do some magic right now, some mathemagics. I'll kind of do a quick example off to the side in blue so you can see. So like if we have something like 3 plus 2 over 4, I'm totally allowed to say this is the same thing as 3 over 4 plus 2 over 4. Instead of finding two numbers of the, not two numbers of the same base, making sure the denominators are the same and adding them together, I can say, hey, if I have two separate pieces of my numerator, I can say that they're each part of their own fraction with the same denominator. So going from here to here, same as going from here to here, just using our fraction rules. We're going to do the exact same thing right here. So pretend this first part's the 3, this first part's the 2, this second part's the 2, and this denominator's the 4. So we're going to bring this into sine of alpha times cosine of beta over cosine of alpha cosine of beta plus cosine of alpha sine of beta over cosine of alpha cosine of beta. So I'm definitely allowed to do this. This is part of our fraction rules. And another reason I want to do this is because I look and I'm like, hey, there's a cosine beta here and a cosine beta here, but I can't cancel those out here because there isn't one over here. Same thing with this cosine alpha and this cosine alpha. So I can't cancel those out because there's not a cosine alpha over here. I can only do that when they're in their separate fractions. So now that I've separated them out, I can say, hey, this cosine beta and this cosine beta, those can go away. And this cosine alpha and this cosine alpha, those can now cancel out. I'm still left with a cosine alpha over here, but I'm able to cancel it out over here because it's just multiplying and dividing top and bottom. So now that we've canceled out everything that we can, we are left with sine of alpha over cosine of alpha plus sine of beta over cosine of beta. And I'm like, hey, you know what? If I look back at my answer, I see we're supposed to have tangent, and I know tangent is sine over cosine. So sine of alpha over cosine of alpha just becomes tangent of alpha, and sine of beta over cosine of beta becomes tangent of beta, and that's exactly what we wanted. This wouldn't work if we had, like, say, sine of beta over cosine of alpha. We need to have the same variable. So same variable over same variable over same variable. So this is a problem that looks like it was a lot, but again, we were able to do it in just a few steps, and now we need to brag about it. So now that we've shown all of our work, therefore, we can say that sine of alpha plus beta over cosine of alpha times cosine of beta is equal to tangent of alpha plus tangent of beta. So we're still going to continue proving in our Go formatives, but keep in mind some of the other problems that we've also done. We'll be practicing a little bit of that as well. Stop by my office hour if you have any questions, and I will see you tomorrow.